introduce the first speaker of this session, so Professor Zabaras from the University of Notre Dame. And so he's going to talk about physics-informed learning for multiscale systems.
Thank you very much, Eric. As they say, I would like to thank the organizers. Okay, so I think I gave a part of this presentation maybe 2 weeks ago, but there has been some new stuff and some stuff that I could not download this morning. The internet was slow. So take everything that you will see as very experimental, has not been published, has not been seen anywhere, so don't take any pictures, no notes, and all of the above. All right. So in some ways, I will follow what Professor Koutsourelakis was talking on Monday's first lecture. So the work is a joint project funded by DARPA between the University of Pennsylvania TUM and the University of Notre Dame. All right, so let me, this concept of physics-informed learning for multiscale systems can mean a lot of different things. In many ways, we try to figure out also what it means to us, because things are moving so rapidly, our interpretation changes with time. Okay? The idea here is to use artificial intelligence, but in a way that rather than generating data from simulations and throwing them in an artificial intelligence like a neural network to do predictions, try somehow to incorporate some of the physics implied by the PDs to the artificial intelligence network, with the hope that we minimize the number of data needed for the simulations. And so I'm going to describe something that I thought this summer it was a major accomplishment, and I remember I communicated with everybody on how excited we were, and 6 months later we decided, yeah, it was exciting, but only for 6 months, because now we have something more exciting. So hopefully I will share that with you today. All right, if I can only make this to move. Did I press any? Bottom, okay, thank you. So we will, I am going to be doing sort of uncertainty quantification and surrogate modeling. So we want basically to learn regression models. We want to learn mappings from input to output, but I would like to do it in a way that I only use inputs, no outputs. Okay, so the Bayesian way is you provide X and Y, and then you learn some mapping from X to Y. And here we would like to do this, if possible, without using any Y's at all, none. And so, of course, if we have data, we can use the data as a regularizer in the process that I will discuss today. And we need also to predict uncertainties. So if we train the model with limited inputs, and we want to do predictions, we need to say something about our confidence in the predictions. And I put this in red here because this is a very murky area in the context of what I'm going to speak. We're not fully Bayesian, and we're not even quite sure what uncertainties mean in the context of what I will discuss today. Okay, because the whole setting has completely changed. So the challenge is that we're interested, we want to model problems that have multiple modes, they're high dimensional, they're multiscale, they're multiphysics, they're nonlinear in the context of the PDs, but also in the context of the mapping from the parameters to the response of the system. So the state of the art basically for quite some time now was maybe 5 years ago, was to use Gaussian processes and these new ideas on sparse Gaussian processes trained with variational methods to do surrogate modeling and uncertainty quantification. But anybody who has worked in this area, they know that you cannot really do more than 100 dimensions, period. You know, anybody who tells you yes, either the effective dimensionality is very small or there is something else they're cooking up. And so I'm guilty in that context as well, because we were thinking too highly of Gaussian processes, but we were limited in the dimensionality. So we would like to use, Bayesian networks, if you like, to do surrogate modeling and uncertainty quantification, but we don't really have a lot of data. So this past summer, we try to address standard problems in uncertainty quantification using Bayesian neural networks with limited data. And I'm not going to tell you exactly how we did it, but we were thrilled because we managed to do up to 4,500 dimensions. So suddenly we went from 100, the same standard problems, to almost 5,000 dimensions. So we were very excited, and I told everybody this is the future, forget Gaussian process, forget this and that. So today, I'm going to do exactly the same problem, but actually with no data at all. So things are moving so fast, and I'm not quite sure where we're going to be tomorrow. Okay, and that's good news, because in some sense, the fact that things are moving fast means there is a lot of momentum and lots of smart people are working in making progress in these areas. So I'm obviously going to integrate in what I'm going to describe the best that neural networks have to offer, including variational autoencoders, normalizing flows, generative models. I will not talk today about GANs, but sort of they are implicitly in the formulation as well. We will like to build these models, as I said, by incorporating as much of the physics as possible, and that's what it will be the essential element, basically, that will minimize the number of data that we need for this sort of models. We will like to use ideas from imaging and convolutional neural networks simply because they are very easy to implement. And if you think of solving PDs, everything is an image at the end of the day, and it's multiple images together that you have to do predictions for. All right, so I'm going to motivate the whole discussion today with a trivial problem. It looks like a trivial elliptic PD, but for those who work in UQ, this is not a trivial problem. So U is the main field variable. For those who understand something about porous media, they can think of U being the pressure, K being the permeability, and tau are the fluxes. You can think of this as velocities. So this is sort of a constitutive equation. This is some conservation equation, some source terms, and the multiscaling comes basically that K is a multiscale field, and it's a random field. So basically, we would like to build a mapping from different realizations of K to the response of the system that includes U and the two fluxes. Let's say if we do two-dimensional problems, Tx and Ty. Okay. So the input is K, and the velocities and the pressure are the responses that we would like to build a surrogate model for. So let's see what else I was going to say here. If we train the model basically with limited realizations of K, somehow we are going to have to say something about the uncertainties induced because of epistemic uncertainties there. And the mapping, obviously, from K to U and tau is highly nonlinear. And so let's see how this thing is going to work. So I'm going to start by reminding you a little bit of finite elements. And if you don't know anything about finite elements, it's good because I will show you how to get finite elements with neural networks today as well. Okay? So this particular problem, if you write it in the context of the pressure alone, you can show that the solution here of the problem is a minimizing of this energy functional. So for those who work in finite elements, this sounds very familiar. Okay? So if you minimize this with respect to U, then you get the pressure U star. And then if you go back to the previous equation I had, if you know U star, you can actually get the fluxes with post-processing. Okay, so this is what I call the primal form because it only involves the elliptic operator and everything is expressed directly in terms of the pressure U. Now you can write this in a mixed form where you involve in the functional both the pressure and the fluxes. So the unknowns basically are tau and U. And you can actually show in this case that the actual solution to the problem, it's a saddle point. It's not really the minimizer of it, but it's a saddle point. Okay, so this is what I will call a mixed formulation for this problem. Now, in case you are curious, not every problem that you can think has a potential that you need to minimize to get the actual solution. I mean, there's a lot of problems with history dependence that this may not be the case, but in principle, if you know the Lagrangian of a system, you actually know everything. Okay, so I will not elaborate more on that, but somehow you can connect this potential with the Lagrangian of the system. There's no time dependence on this, but maybe later I will discuss a little bit on the time dependence as well. So the if you don't have a potential the way I described it before, you can actually sort of define you know, a potential term, like term, but we're not going to minimize it in the same way as you saw before. So this is defined using the residual of the PDE in the primary form. Okay, so it's an integral over the domain of the PDE. So if you give me a U, I can tell you how far away you are from the solution of the system. So in some sense, you will minimize this residual. You can do the same thing in the mixed formulation where you have both tau and U. So this, it's a vector. So if you take the L2 norm, you can have a residual and a mixed residual. And you can even define combinations because these residuals are defined in the spatial domain. You can actually do this adaptively and put more weights on the residuals where, you know, you can think of adaptive finite elements in some sense, right? Where the gradients are very high, you put more importance than in other areas where the gradients are zero. Okay, so I am going to do all of these things with ideas from deep learning. And so the classical way to do this, and there's very recent literature on the topic. It seems actually the literature is so rapidly that some are posting things on archives every other day. Some, they even have patented the names of physics, of AI, and all of these things to be sure that nobody steals their ideas. But ideas are mathematics, and mathematics are shared, right? So nothing to patent there. So one of the formulations is a continuous formulation where you write the response y as some function of the input. S is a location in space. And usually the formulation here, this function of theta, is modeled with a fully connected neural network. I'm going to be showing you actually results for comparison purposes with this, but I would really like to emphasize more the discrete formulation where the response, so if you think of the pressure, it's an image defined in a pixelized form. So ys1 to ysn are basically the values of the response at the different pixels in the image. So the discretization here is given, and you represent the response like this. And we're going to have a few, so we're going to have multi-output. So we may have, y can be a vector. So what you see here, you know, even at each location, I can have the velocity, the velocities, and the pressure as well. So in this discrete case, where we're going to use convolutional neural nets, the response of the system is going to be some function that we're going again to model with a neural network of some latent variables. Okay? And the latent variables, in some sense, you can think they will come in some arbitrary way with some initialization in the process, but we will see how this thing will work like. You can, from everything I told you, since we had this primal variational method and the mixed variational, you can do things with fully connected and convolutional formulations. What you see here, click, means we have tested all of the above, okay? And I'm going to show you in passing some trivial results on solving first PDEs, use these type of formulations, and then we will move to a probabilistic setting hopefully soon after. So some ideas on how things look in the context of the solution. If the log permeability is like this, and you solve this with mixed finite elements, you get a pressure like this, and the two fluxes look like that. So there is a lot of detail here. I mean, this is not extreme variability, but basically you can see we want to actually capture all the details in the solution directly. So the examples I'm going to show you, think of somehow a neural network that you provide me the permeability K looking like this, and you tell me go and compute all of the above. And the way we're going to do it, we're going to introduce a loss function based on the potential formulations that I discussed before, but we will never provide any output training data. So if you do this, it actually literally, with very little work, you can make the fully connected network to work. So what you see on the top are results from the finite element solver, and this is what the network predicts by minimizing the potential. So if you give me, the permeability is not shown here, but basically this is the pressure and the two velocities. The results look pretty good. This is with a fully connected network. The convolutional network, basically, the results are a little bit sharper in this particular case. You can take all possible combinations, and I'm not going to bother you, so I'm going to be clicking a lot. So here it says this is the primal residual in terms of pressure. This is a mixed variation with convolutional neural nets. And the dimensionality of the problems, for example, for this case, it's 4,096 dimensions. Okay, so effectively, this type of problems, if you think, I think the permeability is discretized on 64 by 64. Each pixel, they're literally almost independent of each other. So we don't discretize the Gaussian random field where we sample the permeability. So the dimensionality is about 4,096 in this particular problem. There is an issue that we have not fully resolved. I think it is acceptable now, but if you come and you look at this image, it's very close, in particular for the pressure, you will see a checkerboard effect that appears when you use any of these formulations. Okay? It is not visible from a distance, but it is there. You can, so you can actually see here the solution of the PDE. I have never seen actually these slides, the first time, because I was trying to download things this morning, so it's new to me as well. I did not know it was a movie, but you can see here this fully connected network on this side. This is the CNN. This is basically the finite element solver, and this is what you get with the two formulations solving the PDE. Let me just say a comment, because I mentioned that you don't need to know anything about finite elements. If in the discretization of the potential, if you put the potential to have the form that you get when you discretize things with finite elements, the actual solutions that you get here are exactly the finite element solutions. All right, so if you discretize in the way you do finite elements and you define the stiffness in the potential to be the finite element stiffness, then the solutions actually are the finite element solutions. You never solve any linear equations or anything like that. Okay. The formulation, and again, that's another slide that came out of the blue this morning. It works also for nonlinear problems. It doesn't, you can have the potential defined for the nonlinear case. So here in the Darcy equations, we have dependencies on the velocity modulus squared and velocity cube. It doesn't really, this formulation, it just doesn't care. It can solve nonlinear problems actually exactly the same way. All right. So, so now we want to do a surrogate modeling, and the way that we did this earlier this year was to train the model with different permeabilities X and different responses Y. So we did this as a multi-output regression problem, and then you built a Bayesian neural network with limited data. Again, fully Bayesian because we only have very limited data. But the way we want to do it now is we want to do this in a way that we only know the inputs X. We never give any Y's. There's no Y, all right? So we know the PDs, we know the variation potential. We want basically to build a surrogate model that learns the mapping from X to Y without providing any Y. And we're going to do this again using this these variation formulations. So in one case, we're going to use, so in all cases, X will be this permeability K, and the response will be either directly the pressure or the pressure and the velocities if we use the mixed formulation. So the network, for the particular results that I'm going to show you, looks like this. At least when I left Notre Dame, it was looking like this, but things are, we are playing with different things, but let me just say that whatever gradients we need to compute, we compute them with Sobel filter, not with backpropagation. This is not necessary in the context of convolutional neural nets. So think of the Sobel filter basically implementing derivatives with finite differences plus some smoothing. All right, so how do you define down the potential and all of these things and the residuals in the context of images? So all the operations you see here are pixel-wise operations, and the mean is the mean over pixels. So really these approximations that you see here, it's an integral over the whole domain where you use all the pixel values, right? And when you take the mean, it's an approximation of the integral under the uniform distribution, basically. Okay. So the nice thing is everything manipulates images, and there is nothing to worry, nothing to bother about it. Okay. Straightforward calculations on images defined on pixels. We're going to use metrics basically that they are familiar to you in the context of neural networks, but also since we try to mimic, if you like, finite elements, we're going to use also energy errors, the defined basically having the PD structure in place the same way you do with finite elements. All right, so I'm not going to bother you with the details. You train the model basically, you provide, let's say you have the input, the permeability is a Gaussian random field. So you provide realizations of that random field, okay? And you try to predict what the responses are and learn those responses. And at the end of the day, once the system is trained, you want to be able to provide any realization from that Gaussian random field, let's say, of the permeability, and you want to predict what the output is. And this is what you see on this and the follow-up images. So this is the primal variation formulation. On the top are basically the finite element solutions, and this is what the network gives you, once it is being trained. Okay. So this problem, it's an easy problem. So basically, the permeability. I'm not going to go into the details, but basically you can think that we are using an approximation of the Gaussian random field that has been truncated to 50 terms. So the complexity basically is not very high. 50 random variables basically to define the dependencies in the permeability. And again, you see more of these results and the mixed formulation. Let me just say that somehow when you use the mixed formulation, so you predict 3 channels at the same time, and you use convolutional neural nets and all the standard things in training. This versus doing fully connected neural networks basically is way more accurate, way more faster for these simple problems. Okay, so the convolutional neural nets for us is the right way to go. Okay, so this is, again, as the network is being trained, you can, why not, start doing predictions as the network is being trained, and what you see here is basically predictions on the pressure and the 2 velocities during the training of the system for a permeability that the system has never seen. All right. An amazing result that, again, none of these things have been published. So when I hope, I keep control of my excitement when I see these things, right? But when we did this with Bayesian networks, we could generalize to permeabilities coming from the same random field, right? That's the best you can hope. Somehow here, the system has learned the underlying PDE, and because it has learned the underlying PDE, when you go and you provide the permeability that the system has never seen, in this case, it's analyzed permeability that does not come from the Gaussian random field, it has no difficulties to actually do predictions. And you see this in predictions, basically training with a Gaussian random field and then moving to its analyzed field, and the results look, they look very good. Okay, so keep clicking because there are different cases. The comparison actually with the Bayesian formulation is very difficult to do, and we don't really know yet how to do it, because in one case, in the Bayesian setting, you provide input and output data. In the other one, you provide only input data. So if you give me input and output data, obviously you expect for a small number of training data, this this Bayesian formulation, basically, these blue things, to give you a better convergence properties up to some number of data. But the physics informed, is following close by. And after training with some input, 2 to the power 13th, it completely underperforms. I don't show the graph after that, but it's basically doing way better than the data-driven formulation. But keep in mind, this is misleading because the cost of doing data-driven means you provide the output, and here what you see is there's no output. Okay, there's no output, so so it's a little bit misleading. I mentioned that we could, with a Bayesian setting, we could do up to 4,000 dimensions. We can do all of these problems now without any output in this type of calculations. If you try to extrapolate basically to different random fields and different inputs, and in particular here you can see that's analyzed permeability. This is the L2 error basically that you do when you use test realizations that come from its analyzed field. You can see that the error with the physics-informed model is way better than a data-driven Bayesian model. Okay, the data-driven model does not generalize basically well to data that the system has not been trained. Okay, and in particular, you see the same plot here now, the relative error for the pressure field on analyzed permeability. This is basically the data-driven Bayesian formulation, and this is what you get with the methodology we discussed today. Okay, you can actually use this to compute uncertainties, and it is very easy and rather trivial to do. What you need to do is, since you built the surrogate, you create an ensemble of a certain number of surrogates, and you start doing, once you train the system, you do predictions for each realization of the surrogates that effectively only imply realizations of the parameters in the system. And then each of them, with Monte Carlo, basically you can compute the conditional moments of y given x, like mean, variance, and similar things. And it seems this to be actually quite effective and very inexpensive thing to do. So again, this is, let me see, this is, I suppose, for an easy field of KLE 50, this is what the mean predictions for a permeability that you don't see, and this is what the surrogate basically gives you. This is the error of the two, and this is the error bars that you get from the network. The two things don't supposed to coincide, but they give you a sense of the error bars that you get. You can get PDFs and all of these things with a simple scheme. You can do actually uncertainty quantification. So if you want, you can even integrate completely the probability of X out, and you can compute moments of Y induced by the uncertainty in X, and the results actually look pretty good for all of these cases. All right, so let me discuss briefly a probabilistic version. So all of these things are nice, but we didn't see any probabilities. So how are these things relate to probabilistic models? So if you remember, so what we were doing is we were minimizing some potential. In many ways, you can think that we have the underlying Boltzmann-Gibbs distribution, and effectively minimizing the potential is like sampling from this distribution. Okay, so effectively what we're looking for a methodology that somehow will give some approximations to this Boltzmann-Gibbs distribution that is defined by the underlying potential related to our PDE system. So we're asking, can we learn a distribution in the context of some deep learning framework that approximates this Boltzmann-Gibbs distribution? You can, so the key thing, and Professor Kucherlakis talked on this on Monday, is to obviously do a KL, Kullback-Leibler minimization, but do the reverse minimization problem. So what you do is, this is the exact Boltzmann-Gibbs distribution. Beta is the inverse of the temperature that we still have not fully taken advantage of the algorithmic potential it provides, but P theta is basically the approximation to the network, theta, whatever unknown parameters you have. So you minimize this distance. And when you do that, the expectations that you get are expectations with respect to samples from the approximate distribution. So that's what makes you never to use it removes the necessity of having realizations of y. Okay, you don't have to compute any date of y for little x's. What you need is you need to have the means basically to get approximate y's from the approximate variational distribution p theta of y given x. So the formulation looks, like that. Again, I'm not going to go through all the details. Interestingly enough, the first term, actually, if you neglect everything else, it's basically the potential term. And if you go to minimize that, it's like minimizing the potential. That's what we did before. All right, so you get that sort of as a first term. But interestingly enough, not only you have to minimize the energy, but at the same time, here there is a term that you maximize the uncertainty, the entropy as well. And if, let's say, you want to regularize the problem with some data that you have, you can also put a minus some likelihood term. So at the same time, so you minimize this discrepancy, and at the same time, you maximize the likelihood of the data that you have collected. We use, to be able to calculate these things, there are complications, particularly with the entropy term. So you need to find some variational bound to actually approximate this entropy term. One of the ways to do this is using conditional variational autoencoders. So you basically have to build 3 different networks here. There is a prior model, there is a likelihood model, and there is a posterior for the latent variables, z. There are many variations of this, of what you see and the dependencies. So for example, you can see it here on the likelihood model. You may want to completely remove the dependence on the input x. The results I'm going to show you, they include x, but you can do different variations of this as well. And the implementation is relatively straightforward on training the system. I emphasize again, no data y are provided, only the inputs x. And we already recognize a difficulty, because when we try to solve these problems, the variational autoencoder works very nicely. However, the samples that we get for a given x of y, they're not very diverse. And this goes to this concept of mode collapse that you also get with GANs. So somehow, we were not getting extra information by getting different prior samples from the prior distribution of z. So this, this is the exact y from simulations, and these are different samples. They look very close to each other. So we were not very happy for this problem, okay? We were hoping that we will get some uncertainty, something interesting. And then one of my students in Hangzhou decided to go and do some weird simulations of something that maybe will add some excitement to this problem. So we solved the Allan-Kahn equation that those familiar with phase field methods is a typical model. And the input here is this coefficient alpha, and the output is this scalar u. This problem has 2 stable modes, a negative and a positive stable mode, and it has a whole band of unstable modes in between. So the idea here was, well, you know what, maybe if we sample in different regions of the latent space z, maybe each of those different regions will actually give me samples of the negative stable mode or the unstable modes or the positive mode. And that's exactly what happened. So once you train the system, you build a surrogate that gives you all solutions at the same time. You capture all stable, unstable modes all at the same time. All right? And how is that possible? Well, it is possible because for a given x, you have to sample a z, and depending if you are in different regions of the latent space, that leads to basically different modes in the solution. Okay, so that's very exciting. We have not, we have lots of other little things to worry. So this is something that I'm sure we will investigate further in the days ahead. The formulation that we were playing for in the context of inverse problems is what is called a conditional flows network. And without giving much details here, let me just say that this network, it's fully differentiable and it's fully invertible. So the mapping from x to y and from y to x is 1 to 1. And it turns out that the whole formulation, it is simply a maximum likelihood estimation. So that's also very nice. The calculations are sort of straightforward. You know, in the cascade of the normalizing flows that you have, you basically have to throw out some extra latent variables h in addition to z, so the dimensionality of y matches the dimensionality of h and z. So when we implemented this, there was no actually any issues with mode collapse. Okay, so we, even for these simple problems of Darcy flow, we were able to get a diversity of samples. And you can, you know, so for example, this, what you see here, I think this is the exact pressure for one test permeability, and everything else are samples of the pressure. The same thing here with this is the exact velocity x, the rest are samples. And you can see they're not exactly the same, all right? So there is some diversity of the samples that you get with these normalizing flows. Let me generalize very briefly, because I think Steve talked on this on Monday. All of these formulations are very natural for multi-scale problems. So the idea about multi-scale problems, right, is that, you know, little x, the input, and the little y are high dimensional. We don't really want to coarse-grain simply because we're going to do physics in the coarse-grained space, but we want to coarse-grain as a mechanism of generating more samples of y and x in principle, right? Simply without having to solve, let's say, for a given x, solve a PDE to compute y. So the formulation that fits in very nicely with what I described is basically setting up a target distribution. So you want basically to model the conditional probability of y given x. So these are, again, in high dimensions. And you do this by coarse-graining little x to capital X and coarse-graining little y to capital Y. So effectively, to be able to approximate this, what you need is you need to have a decoder for the response. You need to have an encoder for the high-dimensional input. And then what you need is you need to have some model for how the coarse grain model behaves. You know, what's the mapping from capital X to capital Y. So the formulation, effectively, the variational formulation is very similar with what you saw in these previous formulations. What effectively is you work on the extended space of little x, little y, capital X, capital Y. And the way you see here, that includes also an artificial density that you know, maps you from the high dimensions to low dimensions. And then you have an approximate variational distribution that looks like this. And again, you do a KL minimization, but you use the reverse KL minimization, so you don't require any data whatsoever of little y. So if this is, let's say, a Boltzmann distribution, right, of a molecular system, and I'm going to show you a movie at the end, you don't actually have to do any molecular dynamics. You know, the only thing you would need is to calculate the potential that drives the dynamics of the system. We have not fully implemented this for many problems yet, but the formulation fits in with the examples that you saw earlier in the slides today. Okay, so I'm going to finish with something that I was downloading this morning, because, you know, when a student sends you something and says, please show this because this is very exciting. So I have to show it to you. And don't interrupt me, okay? So I have 5 minutes to go. Let me just tell you what the difficult problem is when you use deep learning to solve PDEs and do surrogate model. If you do, let's say, fluid mechanics, right, and you build a surrogate model and you give me the input X, everybody knows the response can only be modeled adaptively, because there's a boundary layer here, there is something happening on the surface, there's a bulk flow here that nothing is going on. You cannot just go and use a uniform grid the way you do in images and say, and here is my nice response on that, that discretization. It just doesn't work. Certainly it doesn't work for turbulent flows, and I can think actually even multi-phase flows, it just doesn't work. So can you imagine now the following? Imagine that you train a system with some inputs and the outputs defined on the corresponding, let's say, adaptive grid. And now you provide an arbitrary input, and somehow the neural network can understand the physics and spells you the output with the affiliated discretization that sort of has captured the fact that there is more physics here, less here, more gradients there, less there, etc. Can we do that? So the idea here is to, we started playing using geometric neural networks, a concept that has been around the last 2 years or so. Again, you know, there are no equations here. You can use your fully connected, your convolutional neural net the way that I described before, you know. But what you need to do is you need to have some convolutional geometric operators for the input and for the output that somehow try to, you know, whatever geometry you provide, let's say this 1D geometry, it adapts this geometry both for the input and the output so it can best match the physics that corresponds to that particular response. Okay, so and of course you want to do this in a very general setting. So these operations require basically that you use some convolutional patches that map a regular grid to an irregular grid, and these patches basically are defined using Gaussian kernels, but those kernels have to be defined on using geodesic distances, because, you know, when you have discretization, it's not a very dense discretization. You may have a node here, a node there, a node there, so the distances can only make sense with geodesics. So when you do all of these things, and again, I'm going to bypass all these details, we try to experiment, you know, and again, I have only seen these results this morning, to do these variational problems for solving the Burgers equation. And the results I'm going to show you, they don't look very exciting, because I think the discretization used is not obviously sufficient to resolve what is going on. But let me just go directly to one little movie. So the problem looks like this. So we fully convolutional neural net from a fixed grid to another fixed grid, but the input here is basically convoluted, so we can adapt the geometry of the input and adapt the geometry of the output. There are known parameters from these geometric neural nets here, in addition to the ones on the fully connected network. So we are learning all these mappings adaptively. It's like doing adaptive finite elements basically with neural networks without having to guide yourself with anything but the potential that you have seen in the previous formulations. So I don't know how we play this movie. So basically, we're trying to solve the Burgers equation and create a surrogate model for different viscosities. And usually, if you try to do this with neural networks, it will collapse because of the shock wave that you get. So this formulation basically has no issue at all, and it figures out what the geometry, the results with the finite element solver, and I don't know which one is correct or not. You can see there is some discrepancy there, but I think to me that discrepancy something will be very easy to resolve. So there is, I think, this in the context of fluid mechanics, I see lots of potential. All right, so let me just finish. We are working on very many different type of problems in fluid mechanics, did not discuss much about dynamical problems, but obviously we're interested in solving problems with dynamics, and autoregressive modeling plays a role. And I just want to leave you with what is possible, and I believe Steve saw something similar, if not the exact same slide. What you see here is the movie doesn't play because, you know, to play this movie, it will increase the size of the PDF by, 50 megabytes or so. But what you see here is a latent representation of this atomistic system. And I take literally my pen and I move it in latent space in 2 dimensions. And for each location, the system generates realizations in I don't know, what's that, 50-dimensional space or whatever it is. And you can use the actual configurations in this space to compute averages and properties. So if you're interested in this type of work, a recent work to appear in the Journal of Chemical Physics is available. And this implementation, without using any data, it is forthcoming. So we'll be able to implement what I showed you today. Well, it's almost there, okay, without using any molecular dynamic simulations. And I think that's my last slide, actually. And and still on time.
Almost.
Almost.
Thank you.
All right.
I don't have a question, I have a comment, and I would be interested in your reaction to this comment. The way I understand what is presented is, in fact, position 2, which is a matter of trust. Some people trust the equations, the Hamiltonian, the physics, as you said, as good representations of reality. And then the method you showed could be is most likely a breakthrough in solving these equations and making predictions and calculating uncertainties. Other people, more recently, would say that they trust the data, the observation they have, and they do not have the PDEs or the Hamiltonian and do not intend to retrieve them. So we'll use neural networks and machine learning in general to analyze the data they have and train the system, the algorithm, on 75% of the data, test it on 20, and make predictions and analyze uncertainty, same as you do.
I used to do.
These are two positions that one.
So if you were asking me 6 months ago, I was doing all of the above, okay? And we don't look backwards, okay? So let me just say something in the context of learning the Lagrangian without knowing what the equations are from data. So we recently we were working on that problem as well, to actually predict completely implicitly the Lagrangian without the need to ever write down any equations. And if we do actually that with some data that we have, then this formulation follows hand to hand, and the two things come together. So I think there is way too much potential and excitement on all of these things. But the idea here is the data are linked directly with the PDE. So if you're solving a physical problem, you are wasting your time solving the PDE to generate data. That's what I used to do for work, many years. It's not worth it anymore because all this data are embedded in the PDE. Now, if you don't have any PDEs and you only have data, you can work for a bank and become very rich. We cannot afford that in the context of physical applications. So.
Questions? Maybe I have one. Did you try to use that to do stochastic homogenization?
Well, I mean, so you realize that what we do is sort of stochastic homogenization. And one of the things I have always trying to advocate to good PhD students is, can we ever try sort of to explicitly see if, like, when we do this type of coarse graining with this probabilistic frameworks, can we actually find some link between the error bars that you get in homogenization with the ones that nobody has done this, and obviously the two things are of different origin, but if both are data driven, there may be something there that we're missing completely, and I will very much love to see that happening. Yeah, and I don't have an answer, but it is, it's on the back of my mind.
Okay, so thank you again.